All right, good afternoon, everybody. So first, just like everything else, we're going to start with lecture 19 here. So please run the code to download that. While you're doing that, I'm going to make a couple of quick announcements. First, we're going to finish binary search trees in today's lecture, and then we're going to start on a new data structure called an AVL tree. And we're going to address a specific problem about balancing trees to be able to maintain this log n search that we hope to have. So first, I want to point out a couple things involving upcoming due dates and notes. The final pre-internship proposal draft is due on Friday at 5 p.m. So make sure that you first contact your project manager, make sure they have enough time to read it over and give you their feedback, so give them a day or so. And then you should have a meeting with them where you go over the project proposal in detail. So we're making sure that we've accounted for any situation where maybe you've been a little too ambitious and we start identifying realistic things to do in the final 4 weeks. It should be rigorous in terms of you should be doing a good amount of work, something you can be proud of when you're done. But at the same time, we have to make sure that you're being considerate of your other coursework and that you're accounting for everything so we can do a fair amount of work during that time. The other thing that I want you to do, if you have not done so already, please ensure that you've shared your drive with me, because I read over all the project proposals and I'm going to give you my feedback as well. And so some groups I can't get in and see them. The ones that I have seen so far, the write-ups are excellent. You all have a lot to be proud of, and this is something that when I show mentors or show other faculty members, they see what you're accomplishing with that and they're extremely impressed. So please make sure I can see that so I can give you my feedback on the proposals. Thursday, based on some conversations I've had with students, it was always a stressful semester, especially without the break. So one way I'm going to address that Thursday, for those of you who like dogs, the pup fesser will be in the house. I see a lot of fist pumps and a lot of, yep, Aaron, that's right, good job. And then the other thing is, because there's a mini break next Wednesday, I know that sometimes that ends up becoming a de facto reading day. What I will be doing to provide a break during that time is that there will be no lab held during that week. So Monday and Tuesday, no lab, don't show up. I won't be there. You don't have to be there either. And there'll be 2 more labs. The last lab, the Monday and Tuesday of the last week of the semester, there's not going to be a lab there either. So that way you can focus on working on your pre-internship and everything else that inevitably comes up in the final week. Okay, so what we are going to address is, first, we want to talk about the final order of traversal. So the first one I talked about was this pre-order traversal, which we use to say that if I get the nodes in this specific order and I insert them into the tree in this way, this will give me the exact structure of the tree. The next one was we talked about in order, which was our way of getting the actual ordering of elements in the tree. Then we had a post-order traversal, where we can remove elements from the bottom up to make sure we can access everything on the data heap. One quick note on a post-order traversal, so let me quickly draw out a quick tree here. So let's say I do 12, 7, 19, 15, 23, 6, and 8. All right, so there are 2 different ways, if you're looking online, to define a quote-unquote post-order traversal. So you can either go this way, you can either start 6, 8, 7, 15, 23, and 19, and then 12. And that's if you're going left, right, and then middle. The other way to do it is if you do it in the opposite order, which is what I presented in lecture. So if you do 23, 15, 19, 8, 6, 7, and 12. So in my experience, having taught this material, if I do left, right, and middle, it actually confuses students a little more when they're just learning pre-order, post-order, in order about the specific orderings. So I present the right, left, up as a way of helping students convey that just a little easier. When I asked this question on the exam about give me the post-order traversal, excuse me, when I asked for the post-order traversal, please use right, left, and middle. So the correct answer for the tree that I just drew up here would be 23, 15, 19, 8, 6, 7, and 12. Does that make sense to everybody? I just want to make sure that I provide clarity on that. So with a level order, let's say we have 15 and I want to build this whole tree. So I go through this entire process. And what I would like to do is figure out where a tree is, where a value is with respect to the rest of the tree, whether it's higher in the tree or lower in the tree. So a level order traversal, I would say would be 15. And I'd start from left to right. So it'd be 10 and 25. Then I have 6, 12, and then 30. So I have a quick question for you all. Does anybody recognize that pattern that I just used to solve that? Yes. I'm sorry? I'm sorry, one more time, please. From a heap, very good. So we're using a heap to take care of this. So this is max heap and min heap. Now, is there a specific algorithm that we also used to be able to get that specific ordering? So you're absolutely right. If we put this into a heap representation, that's exactly what we would get in the underlying data structure. What was the algorithm that we covered relatively recently that allows us to be able to get this ordering from a tree or a graph? What did I produce here when I came up with this? So let's walk through this again. And okay, I don't see anything in the Slack either. So if I start with 15, right? And then I put the 2 elements that are outgoing, like so. And then if I were to remove 10, we remove 15, and then I investigate the outgoing of 6 and 12, and then I investigate the outgoing of 25, which is 30. What is that algorithm that I just used? If we did it in a graph, and by the way, a tree is known as a directed acyclic graph, what's the algorithm that I just described? Yes. Yeah, that's absolutely right. Breadth first search. So we're going to be using a queue to produce this just like we did in graphs. So this pattern looks familiar. Breadth first search of a directed acyclic graph. A binary search tree is a directed acyclic graph with 2 outgoing nodes. And Tommy, you're absolutely right. Karine has hit on the appropriate data structure that we're going to use, which is a queue. And Kristen has also correctly identified breadth first search. So outstanding job to everybody in the Slack. So when we used, let me go in the chat here, BFS, outstanding. So when we do this and we start putting the elements into the queue, what should we actually put into the queue? What is the value that if I put into an element into a queue and eventually want to produce a breadth first search, so the queue will get popped up and I use that information to get to the next element. So I say, all right, 15 is put in first, right? And then the outgoing are 10 and 25. So the queue initially looks like 15. Then I pop off 15 and do 10 and 25. But then I want to go to 10. And I want to do that instantaneously. So if I want to get that value, what's the value that I should put into the queue? Let me phrase it a different way. If I put 10 in, what's the problem with me trying to just say, all right, give me the location of 10 in the tree? Do I have direct access to that information? Absolutely not. So how would I be able to get direct access to that information? Where is that information stored? So let me check to see if anybody's come up with it on the Slack. If I don't want to put in 10, did you have your hand up, Nikita? No. If I don't want to put in 10, which is data, and think about the name of the course, what else do you think I should put in? Go ahead, Lydia. Sure, so we want to be able to make sure that we know where it is. So we want to get the address of this node, not the node value itself. So what we're actually going to do is we're going to we could do a BST node pointer of queues where we're storing the address. I am putting in void pointer as a way to just do a review of how these actually work. So when I pop off that value off the address, I start out with the address of 15. And then I get the addresses of 10 and 25. Is that it? Yeah, 10 and 25. So when I remove the address of 15 and I say, well, the address of 10 is the next element, I don't need to traverse down the tree to find 10. Does that make sense? I have the address immediately, and therefore that improves the runtime that I would use to be able to produce the level order traversal. So let me show you some code here. In the code that you downloaded and include, we have BST, and it's going to take me a split second, so let me go to the slide where I have that information. Now, initially, I have a print level order where I pass the stream and the root itself. And then what's going to happen is, when I initially get here, the element that's being pointed to, I'm going to create a queue. It's the queue that we wrote, which is based off of the doubly linked list we wrote, which we're going to use to store all this information. So we now see that everything that we've built up to this point can be used to solve this problem. So first, here, the tree root is a BST. So here, in order to do that as void, I just cast a void. Just a reminder, if I made this a queue of BST node pointers, I wouldn't need to do that cast. So when I use this address, I push the initial address. Okay, so it finally opened, thank you. I push the initial address onto the queue. So we see void star 0 is pointing to the location that contains the data 15. So we see data and structure are working together. Then, while the queue is empty, I'm going to set a current pointer equal to the location in memory that's being pointed to by the top of the queue. Does that make sense so far? I'm sorry, the front of the queue. So after this, I'm going to remove that element from the top, and then I'm going to print out the data. And then I'm going to say, well, if current node is not left, I'm going to push that element on. So we see now that I have void 1. And if it's not right, I'm going to push the right element. So now we have void 2. So that is how I'm able to, I get the value to the left, I get the value to the right, and then I get the next element at the top. So it's going to iterate back up, and it's going to go straight to the address of void star 1, which is containing the data value 10. And so this is what I wanted to figure out, and I want you all to think about as you're reflecting and studying on this. The difference between data and structure allows us to be able to make this program run faster. I don't need to go 15, okay, 10, now I found it again. I can go straight there because of our understanding of the address. So from here, I'm going to do the same thing. I'm going to have a pointer point to that location, and then I'm going to remove void star 1 from the queue. And then I'm going to say, well, is 10's left pointer null? It's not, so we're going to put void 3 on the left. I'm going to check the same thing, void star 4, which I call the location of the data containing 12. And then I remove 1 from the queue. So now I'm looking at void star 2. So now I'm looking at this location. Once I'm looking at this location, I'm going to check left and check right. It's going to put the element up there. And then we're going to remove it. We'll check left, it's not there. We check right, and now we put that last node in the location. We do the same iteration through the entire thing. And we're now at the leaves of the tree. And that gives us that order. 15, 10, 25, 6, 12, and then 30. So the assumption in level order traversal on an exam is left to right. Does that make sense? We'll go through a few problems like that here. So I finally got the chat popped up, but yes, the pointer is absolutely right. So what Thomas has said is true. All right, let's go through this whole thing. All right, so the other methods that I have in here that I've provided for you, first is a contains method. A contains method goes through the tree. It evaluates if the pointer's here. So what I'm saying here is I have a pointer and I have some sort of element that I'm trying to find in the tree. So publicly, in the public method, the user just passes the value. Is this value in the tree? And then I pass to the private version that value and the root pointer of the tree. So from there, what's going to happen is if this current pointer is null, that means I got all the way down to the bottom and never found it. Then I say, well, if the data is equal to the element, return true. Here we found it. And so there's two other cases. The first case is if the element that we're looking for is less than the current data. And in that case, I pass current left and that particular data that I'm looking for, which we have there as element. And I do the same thing if it's greater. So either it was null, meaning we got down to the bottom of the tree, that value is equal, which means we did find it and we should return true. Then we have those two other cases. So does anybody have any questions about this? Next one is findMin. findMin, how exactly would I want to find the minimum element in a binary search tree? What's the general algorithm? Yes. I'm picking on you. You're scratching your hand, but I'm going to pick on you anyway. Well, what do you think I should do? I'm sorry, what? Okay, so DFS is a good guess. It's not quite right. We're going to make it a little simpler. But no, it's a good guess. Don't shake your head. It's nothing to be ashamed of. Good guesses are good here. DFS allows us to be able to search between one location and the other. If I don't know what the smallest element is, but I want to find where it is, what I can do is I say, well, I have current pointer here. So that means if I root is null, I didn't find anything. Otherwise, if the node, so let's say I have 15, 10, and 7, right? So I'm going to keep going. This value's left node is null. That means there's nothing smaller. So if I keep going left and keep going left in the tree, and I don't find anything, that means I found the smallest element. And then what I do is I return a pointer to that location. Okay, I do the same thing with find max, except I go right every time. Does anybody have any questions about that? All right, so what I'm going to do now is I have this make test BST3, and what I'm going to do, I'm going to run it, I'm going to show you the code. So what I've done is I've inserted the following values: 15, 10, 6, 25, 30, and 12. So this gives me all 4 elements. And so if I do level order traversal, I see that 15 is at the top. And then I have 10, 25, 6, 12, and 30. We see the post order is 30, 25, 12, 6, 10, and 15. Pre-order is 15, 10, 6, 12, 25, and 30. And in order is 6, 12, 10, 15, 25, and 30. For the find min, what I do is I check to see if that's the least. And then I go, well, it's not null, so I keep going. It's not null, so I keep going. This node is null, which means 6 is my minimum. Doing the same thing with maximum. This one's not null, go right. This one's not null, go right. This one's right is null, 30 is the max. And then contains, I just continue to make those decisions. So here I have 12. So what's going to happen in 12 is 15. 12 is less than 15. 12 is greater than 10. It's equal here, so therefore it contains it. Let's pick another one where I say it's false, which is 40. 40 is greater than 15. 40 is greater than 25. 40 is greater than 35. I'm sorry, 40 is greater than 30. Then we get down to this null pointer. And once I reach a null pointer, that means it's not in the tree. So that's how find min, find max, and contains work. And we see that down here at the bottom. I've printed out that the minimum value is 6 and the maximum value is 30. Does anybody have any questions about that before I continue? Okay, so Here in test BST3, one thing I'd like to show you, and so I'm going to vim into this. I'm going to do vim src test bst3.cpp. And if we go down here at the bottom, what we're going to see is the two methods that I wrote for the tree to return findMin and findMax return a pointer to that address. So it returns the pointer to that location. One thing you can use this for is that if the element is not in the tree and you return a null pointer, you can use that as an error check. So you say, if it's not null, that means I found the element and it's not an empty tree. So if you have an empty tree, you can't possibly have a minimum value. Otherwise, you will. And so we're going to use this later on in the semester. Okay, so there's everything else here. And the first thing we're going to do is we're going to use this to remove elements from the binary search tree. So up to this point, we have learned how to put elements in. And our claim at the beginning of the lecture on this lecture series is that all the elements in the binary search tree, we only have the ones that we need, not the ones that we want to have. Just the ones we need. Anything extra, we want to get rid of it. So the question is, well, how do we get rid of it while simultaneously maintaining the ordering in the tree? So first, the other crucial thing here, and I say the location of the node, is that when we delete an element from the tree, we also must ensure that we free that memory in the data heap. Does that make sense? So we have to make sure it's not in the tree and it can be used by another program, especially if we're doing parallel processing, which you'll learn about a lot more in computer architecture and operating systems. And the final thing is we must maintain the proper data order. If we run an in-order traversal on a tree, we must ensure that it actually gives us the in-order elements. So what if I want to delete 10? Does anybody have any idea on what I would want to do if I want to delete the element 10 from the tree? Yes. Sure, so we can select here and say, all right, one thing we can do is we can do a swap. I can swap 10 and 6 or 10 and 12. You can either do the largest element to the left or the smallest element to the right. So basically what you would do is you would bring 12 up here, and then you would say, all right, I'm going to go down, the time I find the next 12, that's the element I want to get rid of. Or I could do the same thing with 6. I could put 6 here, find the next location, and free that. So now we've maintained the ordering of the tree, and we've freed the memory. So that's saying if I just delete 10, I would lose track of how to find 6 and 12. So what we're going to do is we're going to curse down the tree until we find the location, and then we're going to swap the elements. So what we're going to do is I want you to go to include bst.h, and I'd like you to go to line 234. And in that, we are going to write the full remove method together. And then after that, we're going to work on a problem like you will see on the exam, which is given a set of insertions and deletions, select the level order traversal of the final binary search tree. So when we open bst.h, and it's taking its sweet time today, if you go to line 234, you will see that it says problem 1 starts here. Move that for a split second. Okay, there we go. All right, so here, what's going to go on is we have all of the other methods, findMin, findMax, insert, public, and private. And the way that remove works is that I will make a public call with just const t element. So that's going to be the public version. And the private version, you initially call const t element and root. So let me quickly show that to you before we continue. And you can find that method here. So I have remove And we see that it passes just past that value. And I also have it as a bool. Now, the reason why I have it as a bool is because I want to ensure that if we successfully delete the element from the tree, we indicate to the user that it worked. Otherwise, we can say, oh, no element, that element was not in the tree. We didn't delete anything. Okay, so we have a question in the Slack. Anyone else not have bst.h? Right, so if so the person in the Slack, you can actually run the command wget. Like if you have this here, I'll show you the exact thing you can run to clone it if these things happen. So here, instead of lec19, instead of setup.h, you can just do src bst, I'm sorry, include bst.h. And if you do that from your bst folder, you will have that. So if I get rid of this, if I just press enter, you will see the code that comes up. So if you run that command, it will work. Okay, so let me hide that. Okay, so what I would like you to do is I'm going to go back to 234 where I told you to be. And so the first thing we want to do, actually let me ask you a question. When we're dealing with anything with the binary search tree and we're doing stuff with moving things around, what is the very first thing I want to do every single time? We did it with insert, we did it with find, we did it with pre-order, level order, and post order, and in order. What's the very first thing I want to do with anything where I have a private member and the first thing I call is a pointer? Yes. Check if it's null. Outstanding. And that's what we're going to do. So first check to see if cur pointer is equal to null. Make sure you use equals null here. And in this case, you can just do standard cout element, and quote is not in the tree. And then standard endl. And then the other thing we're going to do, since it's a bool, we're going to say, well, we never found it. It's false. So if I'm looking for anything inside of the tree that's not there, I will get all the way to a leaf, and then I will get to the null pointer of that leaf. And if I get to the null pointer of that leaf, and that means the pointer is null, that means it's not in the tree. Therefore, we need to inform the user that we did not successfully delete from the tree. Okay, so next thing, we're going to check left, and then we're going to check right. So first I want to say if the element is less than cur pointer data, then I want to return remove cur pointer left, comma, element. And so what I'm doing here is, well, okay, we know that we currently have a non-null node, which means I have some sort of data inside of it. So by accessing the data, I can see whether I want to go left or go right. In this case, if the element happens to be less than the data, that means we want to go left in the tree. And here I'm going to say else if element is greater than cur pointer data, then I want to return. What do you think I want to return in this case? So now I'm checking to see if it's right. So someone tell me what the rest of the code should be. What do you think I should put in here? Any guesses? Yes. Absolutely correct. You want to do cur, you want to do remove, cur pointer right, and then element. So now we've accounted for if it's less than, if it's greater than, but now we have one last thing that we need to account for. So I'm going to put this else here, and then I'm going to scroll past the if statement and leave these other two else if and else if statements at the top so people can still see them. So now we are in this situation where we found the node that contains the data that we're looking for. And so now what we're going to do is we're going to walk through this set of steps. And so the first thing we want to do is we have to account for 3 different scenarios. We have to account for if the node has 2 children, if the node has 1 child, and if the node is a leaf. We're going to account for all 3 of those scenarios. So the first thing, we're going to say that if it's this not, if it has 2 children. So we're going to say if curve pointer left is not null, and curve pointer right is not null. Does that make sense to everybody so far? So we now know that this has 2 children. And so if we have that data, what we're going to do in this course, whether if it's the code or if we're on an exam, what we're going to do is we're going to use the maximum value on the left in the instance where there are children here. So what I'm going to do is I'm going to say, well, the current pointer's data, we're going to update that. Current pointer data is going to be equal to find max, and I'm going to say curve pointer left. And so now we're going to use that find max method, and this returns the pointer. And so the last thing I want to do is I want to get the data. Does that make sense? In order to get the data, I am going to dereference it, since the method find max is returning a pointer to a BST node. So I have to dereference it and then say data. So now what I've done is the step that we discussed earlier in lecture, where I took that, we're deleting 12, and we were deleting 10, and I moved 12 up. Well, in this case, because we're finding the maximum on the left, I'm moving 6 up. Does that make sense? So just to redraw it as you all are writing out, in this step, what I've done is I say 12, 6, and 15. Find maximum on the left means I'm getting 6 and moving it up here. And so now I'm setting the current pointer's data to that. And so now I have a duplicate. Does everybody see that? So now what I'm going to do is I'm going to say, well, I'm going to say return, remove, and now I want to keep going. I want to go to the left because that's where I know where the duplicate is. And instead of deleting the old piece of data, which is gone, I got rid of 12. I moved 6 up. So here I want to do curve pointer data. And now what's happened is we have moved the value down into the tree. It is going to be the largest piece of data on the left-hand side of the subtree. And so what I want you to check out is a characteristic. And so let me give you this particular tree. I want to give you 15, 20, 12, 6, and 13, sorry. So let's say I'm deleting 15, and I've elected to swap with 13. So I've moved 13 up. That's this particular line of code. Now, what do I know about this particular node here, other than it's a duplicate? What is a characteristic of that particular node? What do we know? Yes. It is the last one. Both of its children will be null. Does that make sense? So now we want to come up with a situation where we want to actually remove something from the bottom. So we've propagated it down. And so now what I want to say is I'm going to come up with an else if case. In that else if case, we're going to say if they're both null. So if curve pointer left is null, and so make this equals equals, and we'll make curve right equals equals. So in this particular case, the else up here means that I have found a node that contains the data. And now I have this situation where I know it's at the bottom of the tree. And so we're going to combine some concepts here. Does anybody remember how we did deletion in a singly and doubly linked list? If I wanted to find the element, what did I need to do? Does anybody remember that step? Yes. Yep, we had to traverse through the list. And so remember I did that little walking thing? Remember that? And then when I got there, what did I have to do next? This is a crucial step that we're going to replicate here. Yes, go ahead. I'm sorry, can you speak up just a little? Actually, I'll come down to you so I can hear you. What did you say? Absolutely right. And then so we had to set the nodes element, especially in a doubly linked list, we had to get the next and previous. And if we wanted to delete this one, how did I indicate that in code? Do you remember how I did that? Yes. Correct. So so what I described when we did that is we would remove the element, calling free. And so you did great. You did steps 2, 3, and 4. I think what I'm looking for a little more is like step 1. In order to know where that was, I had to create what? I'm giving you a major hint with my finger here. I had to create a specific pointer. And what did I call that in code? Does anybody remember? I called it a temp pointer. I created a temp pointer, and then I freed everything, and then I said free temp. And that freed that memory, and since it was removed from that. So we're going to do that exact same thing here, and we're going to keep doing that as we work on deletion. So what I'm going to first do is I'm going to say, all right, I'm going to create this temporary pointer. I'm going to create BST node with a template and a pointer, and I'm going to call it temp, and that's going to be equal to cur pointer. The next thing is that cur pointer was passed to us by some other node, right? So there's some other node pointing to that location. And before it had something that was pointing to. So I need to free it somehow. In this specific case, what I'm going to say is just like what we did when we realized that we had emptied the singly and doubly linked list. We set the head and tail pointers to null, right? So here what we're going to do is we're going to say cur pointer is equal single equals to null. So now that's pointing, it says I don't have any data that I'm pointing to, but we still have temp in the data heap. So in order to do that, I'm going to call free temp, like so. So let me actually put little spaces in that so it's easy to read. And then I'm going to return true. So what I've done in this step is I now have the element at the bottom of the tree. I'm now pointing in different locations. I check to see that it's null. The element that was pointing to that node is now pointing to nothing. And then using that temporary node, I free it from the data heap. And the moment we go outside of the scope of the method, temp is no longer pointing to anything. It's freed in the registers. So we've freed all the memory. Does that make sense? So we have that accounted for. I do see there's a typing going on in the Slack, so I'll address that question in a moment. So the last case we have here is, well, what happens if I have one child or another child? So let me scroll down to here, and I want to put an else case. So in this else case, this is what happens when I have one or the other. And so I'll draw these two situations. Let's say I have 15 and 10, and the other case is 15 and 18. And in both cases, I want to delete 15. So in the case of 10, and just for the record, both of these, even if 15 is the root, have some sort of pointer pointing to it. So cur pointer here means that we have the node at 15. So free is the one we use because we use new and delete. But in free is working more clearly because that works with the C++ standard template library. So what we're going to do is we're just going to say, so this is cur pointer, C-U-R-R. And what I'm going to do is I'm going to say, all right, I want you to point here. And then I'm going to free this information. I'm going to do the same thing if it's right. We're going to point here, and then we're going to get rid of that. Does that make sense to everybody? So we're going to do this step. We're going to use a ternary operator to do so. So we're going to say, well, first I want to create the temp pointer just like I did here. We're going to say BST node template temp. Temp is equal to cur pointer. So now I'm pointing at that sum location of the memory I want to free. And now I want to update cur pointer. So cur pointer is the location that's pointing to from the node that we had before, whether it's root or a parent node. And so I'm going to say either my conditional is going to be cur pointer left is equal to null. So we have a comparison here. I'm sorry, let me make this not equal so I'm consistent. So we're going to say, well, if cur pointer is not equal to null, then cur pointer should be equal to cur pointer left. I'm sorry, this should be a question mark. That's how ternary operators work. And so what's the last thing I should put here? So basically what I'm saying is I have this situation. If it's not null, I have 15 and 10. And this is cur pointer. And so what I'm saying is that if it's not null, I'm going to update cur pointer here. And so that's what counts for there. So what is the last thing I should type here in this situation? Yes. Cur pointer right, absolutely correct. So in this case, cur pointer right. So if left is not null, then we set cur pointer to cur left. If it is null, we set it to right. So if we have 15, null, and 22, and we have cur pointer, then cur pointer is now going to point at 22. Which means we have two last things we need to do. What are the last elements that we need to do? We now have the pointer, we've updated it, we've circumvented the node that we want to delete. And so what do we want to do here? I'll give you a hint. It's still in the data heap. Yes. We're going to free it. Outstanding. So we're going to free temp. And then last step, we successfully freed it. So what do we say? We tell the user, Lydia's on fire today. We're going to say return true. Outstanding. Does anybody have any questions on the process that I went through to do that? All right, so I'll check to see if it worked in the Slack as well. So we update that. And if you run, let me hide this, clear. We're going to run make. Once you get that done, you can run make test bst4, and I have no return statement, so I did something wrong. Unused parameter cur pointer, so I must have, does anybody see where I might have missed a, oh, you know what? All right, so let's check. Let's go through and see if I did anything wrong. So cur pointer, return false, return good rule. What is the compiler error state? Line 239, no return statement in non-void. So let's look at 239. 239 is if return false. No, that's what I have there. Else if. The file cannot be saved and may be protected. Nope. All right, so let's try this again. I'm going to, does anybody able to, those of you who have it written, is everybody able to run test bst4? Okay, getting a lot of thumbs up. So at least I told you how to write the correct code. So I've got that going for me, which is nice. Then, yeah, sure. And then let's open it again. Okay, so it finally run. It was taking its sweet time updating on the Notre Dame machine. So here, what I have is I initially insert all of these elements, and then what I do is I delete 15, and you can use this code if you like to be able to come up with test cases so you can prepare for the exam. Another thing you can do is that there is this really awesome website, and I'm going to show you. Here I already have the AVL tree version of it, but if you go to binary search tree animation, this website here can help you out too. So you can come up with test cases to work on your own. So here we inserted, so here's all the code there so you can go through. Here's all the cases if you want to go back and study that I just described. So that's all the code. And so initially I have here test BST4, and this is the pre-order, traversal, in-order, post-order, and level order. And so if I delete 15, 12 is going to move up to the top, and it's going to free this value here. So you're going to see 12 show up here, and it's going to move up. So on an exam, the correct answer will have assume left max. Next element, we're going to delete 25. So that was it had 2 children, so we just freed it. Then we want to delete 10, 6 moved up. Then we want to delete 17. We're going to delete 29. You see that it says 29 is not in the tree. And so the question is asked in the Slack, has FileZilla been hanging super bad for everybody else? That actually happened to me. That's why it wasn't updating, because I was looking at an old version of my code. So deleting 31, if I delete 12, it's going to move 6 up. If I delete 6, it'll move 30 up. And then finally, it'll be empty. All right, so if you got that working and you press ls, you'll see prob1.txt is there. And so what I'd like you to do is I'd like you to now work on an exam type problem where for problem 2, it's going to ask you, given a following set of insertion and deletions, select the final level order traversal representation of a binary search tree. So on these type of problems, I want you to assume biggest one on the left. So please take 2 minutes to work on this problem, and then I'll go over to the left, your left, my right, and we will work through the problem together. Okay, first of all, who has the correct answer? Who wants to tell me what the correct answer is? Yes. B is correct. So B is correct, and so now let's prove as to why that's correct. So I want to go over. I'm going to go over to, oh, I see there's 2 comments in the chat. I'll provide the code a little later. So I will stop share, and that should bring up, okay, good. So the ordering that we have here is 22, 7, 19, 34, 8, 31, 36, and 7. So I'm going to draw those up first. And so the way it's going to work, 22, when we don't have any balancing mechanisms, we're going to start talking about this after this problem. This will just always be at the top unless I delete. So you can see that I actually have delete there. So we have 22 and then 17. So 17 is smaller. 19 is larger than 17 but less than 22. Then I got 34. Then I have 8. 8 goes over here. 31 goes here. 36 goes here. And then 7 goes there. So that's the full tree without any deletions. So when I do 22, which one do I replace it with? Based on the assumption in the problem. Which one do I replace it with? Yes. Very good. I want to take 19, which is the largest value on the left, and move it up here. So now we have maintained the ordering of the tree. And now I want to delete 31. So now 31 is here. And so the level order, so when I ask the question on the exam, I'll be also evaluating your ability to understand what the level order traversal of the tree is. So the level order, we start at the top and we go left to right, just like we went through. So it would be 19, 17, and 34. 19, 17, and 34. Then 8 and 36. And then 7. And so that's how we work through that problem. All right, does anybody have any questions about that? Yes? Is it 34 instead of 31? All right, so let me put 31 back in. So 34 will move 31 up here. And so this in the traversal becomes 17, 19, 17, and 31. Any other questions? I'm going to go back up and check the Slack too. Okay, no questions in the Slack. Yeah, sure, what's up? 19, so we made that decision. That was the assumption of maximum value on the left-hand side. So what happened over here was 19 was, we initially had 22 at the top, and then 19 was over here. So it's the find max on the left. So that's what we did in code. So on an exam, I would ask you to assume that it would take the maximum value on the left, which would be here. Got it? Awesome. Any other questions? Okay, so the next thing we're going to do is we're going to address a challenge here with a binary search tree, which is, well, what happens when the user puts everything in order? So one thing I say is never assume that the user is going to do everything you want to. If it's a random set of numbers, it will come out great. But what happens if I say, all right, I'm going to insert 15, then 25, then 30, then 40, and then 50? What ends up happening is it becomes a glorified linked list. But even worse, we have a bunch of left pointers in this case that are just null. So we have all of the drawbacks of a doubly linked list and all the drawbacks of a singly linked list with none of the benefits of a binary tree. And so this problem starts getting investigated in the 1960s. 1962 is when AVL trees were presented. And they're trying to figure out the best way to do searching in these low memory environments. So it's a compromise between the memory of the linked lists, but also the speed of hash tables. So let's take a first crack at trying to balance this tree, this 15, 25, 35, 45, 50 tree that I did. So let's say I did these first three. So I have 15, 25, and 35. What do you think would be the simplest way to kind of address this? if I wanted to balance the tree. Yes. We want to somehow make 25 the root. So if I drew it out, it would become 25, 35, and 15. What we're going to do is we're going to call this a single left rotation. And the way it's going to work is I'm going to say, well, this is, let's say, grandparent, parent, and child, right? And so 25 also has some sort of node here. 15 does as well. And we have to maintain the ordering those even if they're null. So what's going to happen is we're going to say, all right, 15's right child becomes what's ever here. So if this was 20, it would still be maintained. And then 25's new left child would become 15. So that would become 25, 15, 20, and 35. Does that make sense? So we're going to go through this process of doing insertions and what we're going to call rotations. So the way we can tell this is by knowing what the balance is on each element in the tree. So here at pointers, both are null, therefore the balance, the height is 0. I move up here to 1. It's 1 on the right, 0 on the left, and here it's 2 on the right and 0 on the left. The rule for AVL trees is that no node may have an imbalance of greater than 1. So here we have 0 and 2, and therefore we've reached imbalance. So now I know, oh hey, I have 2 this way, 0 that way. I need to rotate in order to provide balance for the tree. Does that make sense so far? So based on that, I'm going to use a set of rules. We're going to rotate left just as was proposed, and we make it look like that. And so this is known as tree balancing. AVL trees are going to be the first crack at it, and it's going to provide a very strict balancing. We have a guaranteed big O log of n insert and big O log of n search and big O log of n delete. However, there's a trade-off. The trade-off is that the mechanisms to actually do this are much more complex. And the ways in which we can get around that are what's going to motivate the next 2.5 weeks of lecture. But the reason why it's important for you to know AVL is because it's a strict log tree. In algorithms, when you take that class and you're asked, like, what data structure should be used if I want guaranteed log n search or find to do a specific task? If you say red-black tree or binary search tree or B tree or splay tree, you'll be wrong because it's not guaranteed. In an AVL tree, it is guaranteed. So that's what we're doing here. We're going to talk about how to guarantee this. So we're going to have everything in the BST node plus the height. So we're going to have an internal value. So we're going to create an AVL tree node that has that value. So if I go back here and if I say vim include AVL node.h, you're going to see that the struct members have all the 3 elements that we had before, as well as a new private member height. Now, to give you a preview, the reason why it's called int height instead of unsigned int height is because if I want to be able to subtract them, and if I have left is greater than right, it'll be positive. But if right is greater than left, it will come out negative. And if we use unsigned int, we're going to get a massive overflow. Does that make sense? So we want to make sure that we're keeping track of everything in terms of data and to ensure that we can represent everything later on in our problem. In the constructors, it's the same thing, except with height. The destructors, the same thing. I'm doing right and then left, as I explained at the beginning of lecture. I do the same thing with the copy constructor, except I've added height here. And in the assignment operator, I've done the same thing for both the node assignment operator and the pointer that we did. Okay, so there's all the code I just showed you. So now what I want to do is I'm just going to say make test AVL1. And what this is it contains all the same code that of the BST. So the only difference that I've made is in AVL tree 1.h, And again, FileZilla seems to be hanging up. So I'm going to run vim include avl tree 1.h. And you can see for insert, it's the exact same code. Copy tree, it's the same code. Print in order, it's the same code. So it's the exact same thing. The only thing is I've set up by adding height to check to make sure that my reconstruction of that node propagates properly, so it doesn't have any unintended consequences. So then in AVL tree, what we're going to do is we are actually going to work through and write the insertion method. So there are 4 different rules that we're going to use for balancing AVL trees. This one is going to represent what I just drew out, and it's going to be the single rotate left. So here I have the current pointer is pointing to A and B, and I have some sort of imbalance where the right height is 2 greater than the left. And so I identify the grandparent, parent, and child, and here are the 4 steps. I want to make sure that I have everything taken care of. So first I'm going to say, well, parent's right child needs to be pointing to child's left child, which is the value y. If we did that in order, we would see that the in-order traversal would give us x, a, y, and b. So by moving that, we still have the same in-order traversal. Does that make sense? So we have not lost the integrity of the traversal. So now what we're going to say is B's left child is now going to be A. And then I'm going to move cur pointer from A to B, because now it's going to say, it's going to point here, and now B will be pointing to A, which will have X as its left child, we'll say Y as its left child, X as its left child, Y as its right child. And so it'll look like this. So let me complete the animation. And when that's done, it will look like that. Does that make sense? The second rule is going to be the exact same thing, but to the left. Here I will make A's left child equal to B's right child, so that's parent and child. Now child, which is B, that's right child is going to become A. And then I'm going to move cur pointer over to B. So from there, if I'm doing this 15, 25, and 35, so first, does anybody have any questions on this? Because I'm going to replicate this through animation, and then we're going to actually work on, yes, Nikita. Yeah, so the question is, how are we setting the child? I will show you in a moment. Okay, so what's going to happen is, I'm going to do 15, 25, and 35. So what's going to happen is, I am going to recurse up the tree. So when I get here, and I'm going to show you all this, precisely how this is done in a moment. What's going to happen is I get to this situation where 0 minus 2 is going to be equal to -2. Since it's less than -1 here, that means we have an imbalance. So now what's going to happen is I'm going to point to grandparent, parent, and child. And so when I recurse this way, it will know that I went in this direction. So now what I want to do is I'm going to have the root come here. So the way it's going to work is that even though this is null, 15's right child is going to point here. Then 25's left child is going to point here, and then root is going to be moved there. So those are our 3 steps. So you're going to see 15 gets updated, so does 25, and now root moves there. And then this is what it will look like cleaned up. So now we have that balance. So the next step is, let's insert 3 more. We're going to do 10, 7, and 6. So I do 10, everything looks fine. And now I'm going to have 7, and we see that the violation occurs here. So now we'll do the rotation. The grandparent here has this pointer, and this pointer is eventually going to want to point to 10. 10's right child is going to point to 15, and 15 is going to point to what 10's left child was, which in this case is null. We update 25's pointer, and when it's cleaned up, it looks like that. Does that make sense? So then if I do 6, we now see that I have the violation here. And so now, which do we choose? Grandparent and parent, but where is the child? And so Nikita, this is where I'm going to get to your question, which is how do we know where the child is? The child is, we identified this because it came from the left in recursion. So when we recurse left, we're going to have that case where we're going to perform a balance. And so that's how we know where it came from. So from there, I'm going to say, well, all right, I move 25's left child to be 10's right child, which is 15. I move 10's right child to point at 25, and then I update the root to point at 10. So when I clean this up, the way it's actually going to look, it's going to go root. They'll say 10. 10's right child is 25. 25's left child is 15. 35's over here, and then 10's left child remains the same at 7 and 6. Does everybody see that? And there's the resulting tree. And now I'm going to do 12. So if I insert 12, that comes here. 12, there's no violation. But now when I insert 13, this is where we have a violation. So what's going to happen is I would want to do this rotation. So I would say, all right, 25 is going to be here, but we have an interesting case where both of them we were doing here, but now this one's a zigzag. And we're going to call this a double rotate. And I'll describe how to do this in a moment. What we're going to do is we're going to say, well, 13 is greater than 12 and less than 15. So if I want this to be our subtree, 13, 12, and 15 is going to have the balanced version of this. Does everybody see that? So if I'm able to do this, then 13 should be pointed to by 25. So you're going to see that 13 comes up like so. And now if I put in 14, my violation occurs here. So now I have to account for all these scenarios. So if I do a right rotate at 25, we have a problem. And we're going to address this double rotation in a moment. So if I try to say, all right, I'm going to say, all right, I'm going to put 10 here and point at 13. 13 is going to point at 25. 25 is going to point at 15. What will happen is we don't actually solve the imbalance. So what we need to do instead is we need to come up with this double rotation. And so the way this will work is I want to move 15 up so that way it's in the middle. And here is the first rule. So let me walk you through these two steps. The first rule is double rotate right. Notice the ordering that A, parent, B, child, C, grandparent, and D is the in-order traversal. So what's going to happen is I'm going to update it so that way first the root's going to point at the new child. Then child is greater than parent. So what we're going to do is we're going to exchange parent and child. Does everybody see that? So that's the next step. Parent and child. But here's the other thing. Child, with the CH, is less than C and less than parent. I mean, than great-grandparent, in this case, GP. So in this case, the proper ordering is child, C, grandparent. So what's going to happen is grandparent, instead of pointing here, is now going to point to C, and child is now going to point to grandparent. So now that actually becomes child. Sorry, this will be child. Let me update this, sorry. So child's right child is going to be grandparent, and grandparent's left child is going to be C. So it'll look like this. Does that make sense? And so what's going to happen is once we do all this, it's going to move child up here, and it will look clean like that. So this is before, and this is after. So now we're going to say, all right, we're going to double rotate left. We're going to do the exact same thing. Root's going to point at the child. Parent is going to point to, parent's left is going to point to child's right. Child's right is going to point to parent. Grandparent's right is going to point to child's left. And child's left is going to point to grandparent. This will move child up, and therefore this will be the before and after. Does anybody have any questions on this? We're going to work through example, and then I'll be going over code probably next lecture. All right, so back to the problem. Now I'm going to say, all right, 10's right child is going to be now 15. And now 25's left child is going to be, well, first we're going to do parent. So 13's right child is going to become 14. 15's left child will become 13. The next thing, we're going to say that 25's left child will become 15's right child, in this case, which is null. And then we're going to make 15's right child 25. And that will move it up and be clean like this. And so what I'm going to do, since we only have 3 minutes left, is we're going to do problem 3. And I'm going to run make prob 3, and we're going to work through this together. And the way you can see this simply is to go to an AVL. Let me hide this. Hide blend neutral. So AVL visualization. So we're first going to insert 30, 20, and 10. So what's going to happen is we're going to get 30 and 20. And now 10 is going to be the left child of 20, which means we're going to do a left rotation. So watch what happens. We're going to rotate. It's going to identify the error here, and it will rotate left by 1. Does everybody see that? So now we're going to insert 45. So 45 will become the right child of 30, and we're not going to have any imbalance that violates the rule, so we're good. We're now going to have 50. And what you'll see in a problem I ask like this on an exam is I'll ask you to identify a single left rotation, a single right rotation like we just did here. And then after inserting 50, I want to insert 55. And so now what's going to happen is and you can scroll down here and pause. So I'm going to pause there for a moment. I'm going to zoom out. And what we're going to see here is that we now have the imbalance here. It's 3 on the right and 1 on the left. So we're now going to identify this opportunity here. We're going to see that the root is the grandparent, the parent is 20, and the child is 45. So 20's right child is going to become 45. 45's left child is going to become 20, and it will rotate over like this. So let me step forward, and that's exactly what happens. So next, what we're going to do, we're going to insert 6, 5, and 4. So we're going to see that when I insert 6, let me skip forward, insert 6, it's going to become the left child. I'm going to press play. It's going to become the left child of 10. And at this point, we don't have any violations. When I do 5, we're going to see that the error is going to be here. And it's going to move 6 up here. 10 is going to become the right child of 6, and 5 will be the left child of 6. And so let me press insert. There we go. And then last, I want to insert 4. And so I'm going to press pause when we get to the violation. It's going to go up here. And now here we are. We have 3 on the left and 1 on the right. So now what it's going to do is it's going to rotate right to account for this. So I'm going to step forward, identifies this, and we rotate here. It's going to make 6's right child is going to become 20. 20's left child is going to become 10. And so 45 will now be pointing at 6. So I step forward, and that's exactly what happens. And I believe that was it. So the in-order traversal is 45, 6, 50, 5, 20, 55, 4, 10, and 30. And if we look at this, we see that 45, 6, 50, 5, 20, 55, 4, 10, and 30 is choice A. And if you run this and run test.h, you will see that you earn 95 points towards your in-class assignment. So we will start lecture by going over in more detail an AVL problem. I will review the code, and then we're going to discuss, well, how do we get around requiring balancing mechanisms that know the full balance. So we're going to come up with what's known as a greedy approach, and our first attempt at that will be called a B tree. If there are no other questions, then you are all dismissed, and I will see you on Thursday, unless you have lab, then I'll see you later. All right.